Alrighty. Left off last night listening to the recitation. Finished that. I also did a little bit of listening to a separate set of lectures that are on YouTube that mirror the ones on their website. I was listening to those at the gym this morning, just on floating point, because that's what we're going to start the reading on. My goal today for the reading is just to do the reading. It's not slow down with the problem sets unless they actually really interest me. So I'm going to vim up the, it's not what I wanted, problems for chapter 2. And I'm only going to do the ones that actually interest me for floating point. So let's start reading. Floating point representation encodes rational numbers, so numbers with a fractional part, of the form v is equal x times 2 to the y. Is useful for performing computations involving very large numbers. The absolute value of v is much greater than 0. So v is the value, is equal to x, which is the fractional part, basically, times 2 to the power of x, which is exponent. So you have the exponent and the mantissa. So it's 1 dot mantissa times 2 to the power of exponent, with a sign bit and some caveats around things like positive, negative infinity, 0 values, nans, and the difference between what do they call it? Normal values and non-normal values. I forget what the exact terminology is, but I'm sure we will get to that pretty soon here. The Institute of Electrical Electronics Engineers, IEEE, is a professional society that encompasses all of electronic and computer technology. It publishes journals, sponsors conferences, and sets up committees to define standards on topics ranging from power transmission to software engineering. Another example of an IEEE standard is the 802.11 standard for wireless networking. Numbers, so very large numbers very close to 0, and more generally as an approximation to real arithmetic. So generally they behave better under situations like overflow, because when you overflow a float, you get stuck in infinity basically. So you don't wrap around back to 0 or to a negative number. So when you're programming, it's a little bit easier to deal with those edge cases. Up until the 1980s, every computer manufacturer devised its own conventions for how floating point numbers were represented and the details of operations performed on them. In addition, they often did not worry too much about the accuracy of the operations, viewing speed and ease of implementation as being more critical than numerical precision. All this changed around 1985 with the advent of IEEE Standard 754, a carefully crafted standard for representing floating point numbers and the operations performed on them. This effort started in 1976 under Intel's sponsorship with the design of 8087, a chip that provided floating point support for the 8086 processor. Intel hired William Kahn, a professor at the University of California, Berkeley, as a consultant to help design a floating point standard for its future processors. They allowed Kahn to join forces with a committee generating an industry-wide standard under the auspices of the IEEE. The committee ultimately adopted a standard close to the one Kahn had devised for Intel. Nowadays, virtually all computers support what became known as IEEE floating point. This has greatly improved the portability of scientific application programs across different machines. In this section, we will see how numbers are represented in the IEEE floating point format. We will also explore issues of rounding, when a number cannot be represented exactly in a format, and hence must be adjusted upwards or downwards. We will then explore the mathematical properties of addition, multiplication, and relational operators. Many programmers consider floating point to be at best uninteresting and at worst arcane and incomprehensible. We will see that since the IEEE format is based on a small and consistent set of principles, it is really quite elegant and understandable. Fractional binary numbers. A first step in understanding floating point numbers is considered binary numbers having their fractional values. Let us examine a more familiar decimal notation. Decimal notation is a representation in the form dm all the way to d0, and then d negative n. Okay. And then we get this little diagram, which is the fractional binary representation. Digits to the left of the binary point have weights of 2 to the I, while those to the right of the have weights of the form, it would be 2 to the negative I, basically. Python 2 to the negative 3 is equal to 2, or 1 divided by 2 to the third. True. Each decimal digit d ranges between 0 and 9. This notation represents a value d defined as 10 to the power of I times d to the sub I. And then you sum all the d's, or d sub i's, and you get the value of d. The weighting of the digits is defined relative to the decimal point symbol, meaning that the digits to the left are weighted by non-negative powers of 10, giving integral values, while the digits to the right are weighted by negative powers of 10, giving fractional values. For example, 12.34 represents number 1 times 10 to the 1, plus 2 times 10 to the 0, plus 3 times 10 to the negative 1, plus 4 times 10 to the negative 2, or 12 and 34/100ths. By analogy, consider a notation of the form so-and-so, binary numbers, where each binary digit or bit, bi, ranges between 0 and 1, as illustrated in figure 231. This notation represents this number b defined as b is equal to the range of negative n to m, where we basically take the sum of that range, where each element of that we visit, we take the binary value and multiply it times 2 to the power of I. The symbol dot now becomes a binary point with bits on the left being weighted by non-negative powers of 2, and all those on the right being weighted by negative powers of 2. For example, 1011.112 represents number so-and-so. One can readily see from equation 219 that shifting the binary point 1 position to the left has affected dividing the number by 2. For example, while 101.11 represents the number 5 3/4, 10.111 represents the number of 2, basically half of it, 2 and 7/8. Similarly, shifting the binary point 1 position to the right has affected multiplying the number by 2. For example, this number represents number 11.5, so it would be 22/23, would be the double. Oh, but we're bringing up from the previous value. Okay. All right. Note that numbers from 0.11 onward represent numbers just below 1. For example, 0. All ones represent 63/64. We use the shorthand notation 1 minus e epsilon, I guess, to represent such values. Assuming we consider only finite length encodings, decimal notation cannot represent numbers such as 1/3 and 5/7 exactly. Similarly, fractional binary notation can only represent numbers that can be written as x times 2 to the power of y. Other values can only be approximated. For example, number 1/5 can be represented exactly as a fraction decimal number, which is 0.2. As a fractional binary number, however, we cannot represent it exactly. Instead, must approximate it with increasing accuracy by lengthening the binary representation. Makes sense? Fill in the missing information in the following table. Not going to do that. So this is 2.45. We're going to do a good old skipperoonie on that one. Practice problem 2.46. The imprecision of floating point arithmetic can have disastrous effects. On February 25th, 1991, during the first Gulf War, an American Patriot missile battery in Dhahran, Saudi Arabia, failed to intercept an incoming Iraqi Scud missile. The Scud struck an American Army barracks and killed 28 soldiers. The U.S. General Accounting Office, the GAO, conducted a detailed analysis of the failure. 76. It determined that the underlying cause was an imprecision in a numeric calculation. In this exercise, you will reproduce part of the GAO's analysis. The Patriot system contains an internal clock implemented as a counter that will increment every 0.1 seconds. To determine the time in seconds, the program would multiply the value of its counter by a 24-bit quantity that was a fractional binary approximation to 1/10. In particular, binary representation of 1/10 is the non-terminating sequence so-and-so, where the portion in brackets is repeated indefinitely. The program approximated 0.1 as a value x by considering just the first 23 bits of the sequence to the right of the binary point. Oh, we're dealing with clock drift here, okay. Normally, a slight error in the absolute time reported by a clock reading would not affect a tracking computation. Instead, it should depend on the relative time between two successive readings. The problem was that the Patriot software had been upgraded to use a more accurate function for reading time, but not all of the function calls had been replaced by the new code. As a result, the tracking software used the accurate time for one reading and the inaccurate time for another. That's a bummer. IEEE floating point representation, positional notation. So I'm going to skip this one as well. So this is 246. I mean, it seems fun. Like I could do that, but I want to make progress on the reading here, so I'm going to accelerate my reading. Skip. Maybe come back. Okay, positional notation such as considered in the previous section would not be efficient for representing very large numbers. For example, the representation of 5 times 2 to the 100 would consist of a bit pattern of 101 followed by 100 zeros. Ugh. Instead, we would like to represent numbers in the form of x times 2 to the y by giving the values of x and y. The IEEE floating point standard represents the number in the form of values equal to -1 of the sign bit times the mantissa. Actually, yeah, but the mantissa is encoded times 2 to the exponent, and the exponent is also encoded. The sign s determines the number is negative or positive, where the interpretation of the sign bit for numeric value 0 is handled as a special case. The significand m is a fractional binary number that ranges either between 1 and 2, or between 0 and ranges either between 1 and 2 minus epsilon, or between 0 and 1 minus epsilon. Yeah. Depending on whether it's close to 0 or not. The exponent e weights the value by a possibly negative power of 2. The standard floating point formats, a little diagram here. Boop, boop, boop. So you got single precision, double precision, where single precision, you got 8 bits. For the exponent, double precision, you have 11 bits. And there's 64 bits in doubles. Standard floating point formats, floating point numbers are represented by 3 fields. For the 2 most common formats, these are packed in 32-bit single precision or 64-bit double precision words. The bit representation of a floating point number is divided into 3 fields. To encode these values, the single sign bit S directly encodes the sign S. The k-bit exponent field encodes the exponent E. The n-bit fractional field encodes a significant M, but the value encoded also depends on whether or not the exponent field equals 0. Yep. Figure 232 shows the packing of these 3 fields into words. For the 2 most common formats, in the single precision floating point format, a float and C, field S, exponent, and fraction are all 1, 8, and 23 bits each, yielding a 32-bit representation. In the double precision floating point format, a double and C, S, exponent, and fraction are 1, 11, and 52 bits each, yielding a 64-bit representation. The value encoded by a given bit representation can be divided into 3 different cases, the latter having 2 variants, depending on the value of exponent. These are illustrated in figure 2.33 for single precision format. This is the most common case. So these are normalized values, they call them. So these are values between 1 and 2 for the significand or mantissa, and a non-zero value for the exponent. It's the most common case. It occurs when the bit pattern of exponent is neither all zeros nor all ones. Numeric value 255 for single precision, 2047 for double. In this case, the exponent field is interpreted as representing a signed integer in biased form. That is, the exponent value E is E minus the bias, where E is an unsigned number having bit representation so-and-so, and bias is a bias value equal to 2 to the power of k minus 1 minus 1. 127 for single precision, 1023 for double. This yields exponent ranges from negative 126 to positive 127 for single precision, and negative 1022 to positive 1023 for double precision. The fraction field frac is interpreted as representing the fractional value, where 0 is less than or equal to f is less than 1, having binary representation so-and-so. That is with the binary point to the left of the most significant bit. The significand is divided to be m is equal to 1 plus the fractional bit. This is sometimes called the implied leading 1 representation, because we can view m to be the number with binary representation so-and-so. This representation is a trick for getting additional bit of precision for free, since we can always adjust the exponent E so that significant m is in the range 1 less than or equal to m is less than 2, assuming there is no overflow. We therefore do not need to explicitly represent the leading bit, since it's always equal to 1. Well, not always. You could have values below 1 when the exponent is 0. So these are the categories. So you have denormalized values where there is no implied 1. So you have infinity, you have nans, you have denormalized, and you have normalized. Okay. It is interesting that they waste so many bits on nans. Denormalized values, when an exponent field is all zeros, represent number is denormalized form. In this case, the exponent value is E is equal to 1 minus bias, and the significand value is m is equal to f. That is the value for the fraction field without the implied leading 1. Denormalized value numbers serve 2 purposes. First, they provide a way to represent numerical value 0. Since with a normalized number, we must always have m is greater than or equal to 1, and hence we cannot represent 0. In fact, the floating point representation of 0, positive 0, has a bit pattern of all zeros. The sign bit is 0, the exponent field is all zeros, indicating a denormalized value, and the fractional field is all zeros, giving m is equal to f is equal to 0. Curiously, When the sign bit is 1, but all of the fields are 0, we get the value -0. With IEEE floating point format, the values -0 and +0 are considered different in some ways and the same in others. I mean, numerically they're the same, but let's actually look at this diagram in the side before we continue on. Wait a minute, where did I go wrong here? Here we go. Why set up the bias this way for denormalized values? Having the exponent be 1 minus the bias rather than simply minus bias might seem counterintuitive. We will see shortly that it provides a smooth transition from denormalized to normalized values. Okay. Let's see. A second function of denormalized numbers is to represent numbers that are very close to 0. They provide a property known as gradual underflow, in which possible numeric values are spaced evenly near 0. Special values, case 3. A final category of values occurs when the exponent field is all 1s. When the fractional field is all 0s, the resulting value represents infinity, either positive or negative depending on the sign bit. Infinity can represent results that overflow, as when we multiply two very large numbers or when we divide by 0. When the fraction field is non-zero, the resulting value is called a NaN, short for not a number. Such values are returned as the result of an operation where the result cannot be given as a real number or as infinity, as when computing square root of -1 or positive infinity minus infinity. They can also be useful in some applications for representing uninitialized data. Example numbers. Figure 2.34 shows a set of values that can be represented in a hypothetical 6-bit format having k is equal to 3 exponent bits and n is equal to 2 fractional bits. The bias is 2 to the 3 minus 1 minus 1, which is 3. Part 1 of the figure shows all representable values other than NaN. The two infinities are at the extreme ends. The normalized numbers with maximum magnitude are positive negative 14. Denormalized numbers are clustered around 0. These can be seen more clearly in part B of the figure, where we show just the numbers between -1 and +1. The two zeros are special cases of denormalized numbers. Observe that the representable numbers are not uniformly distributed. They are denser near the origin. Figure 235 shows some examples for a hypothetical 8-bit floating point format. Okay, before we move on to that figure, I just want to look at this figure. So you have the denormalized, which are diamonds, which I don't see. The normalized, these are all normalized, and then you got infinities at the end. And then denormalized show up in between the range around negative 0.2. I thought they went all the way from interesting. Representable values for 6-bit floating point format. These are k is equal to 3 exponent bits and n is equal to 2 fraction bits. The bias is 3. Okay, let's reread that paragraph then. Figure 235 shows some examples of a hypothetical 8-bit floating point format having k is equal to 4 exponent bits and n is equal to 3 fraction bits. The bias is 2 to the 4 minus 1 minus 1 is equal to 7. The figure is divided into 3 regions, showing regions representing the 3 classes of numbers. The different columns show how the exponent field encodes the exponent e, while the fraction field encodes the significant m, and together they form the represented value v is equal to 2 to the e times m. Closest to 0 are the denormalized numbers. Starting with 0 itself, denormalized numbers in this format have e is equal to 1 minus 7 is equal to negative 6, giving a weight of 2 to the power e is equal to 1 over 64. The fractions f and significance m range over the values given giving numbers v in the range of so and so. Okay. Example, non-negative values for 8-bit floating point format. Observe the smooth transition between the largest denormalized number and the smallest normalized number. The smoothest is due to our definition for E for denormalized values by making it 1 minus bias rather than minus bias. We compensate for the fact that the significant of the denormalized numbers does not have an implied leading 1. Makes sense. As we increase the exponent, we get successively larger normal values, passing through 1 and then to the largest not normalized number. This number has exponent e to the 7, giving a weight of 2 to the e is equal to 128. The fraction equals 7 over 8, giving a significant m is equal to 15 over 8. Thus, the numeric value is v is equal to 240. Going beyond this overflows to positive infinity. One interesting property of this representation is that if we interrupt the bit representation of values in figure 235 as unsigned integers, they occur in ascending order, as do the values they represent as floating point numbers, except for negative infinity. This is no accident. The IEEE format was designed so that floating point numbers could be sorted using an integer sorting routine. A minor difficulty occurs when dealing with negative numbers, since they have a leading 1 and occur in descending order, but this can be overcome without requiring floating point operations to form comparisons. Yeah, just a mapping. Okay, now we got another problem that I'm going to skip because there's a big freaking table. Consider a 5-bit floating point representation based on IEEE format. Yeah, I'm not going to do that. Just a big table. So it was at 47, 247. 247, skip. Okay. Figure 236, which is at the bottom of the page, shows the representation and numeric values of some important single and double precision floating point numbers. As with 8-bit format shown in figure 235, we can see some general properties for a floating point representation with k-bit exponent and an n-bit fraction. The value 0 always has a bit representation of all zeros. The smallest positive denormalized value has a bit representation consisting of a 1 in the least significant bit position, and otherwise all zeros. It has a fraction and significant value. M is equal to F, which is equal to negative n. Next exponent value is equal to 0, which would be negative 2k minus 1 plus 2. The numeric value therefore has, okay. The largest denormalized value has a bit representation consisting of an exponent field of all zeros and a fraction field of all ones. It has a fraction and significant value, which we have written as 1 minus epsilon, and exponent value so-and-so, the numeric value blah blah. Smallest positive normalized value has bit representations with a 1 and least significant bit and an exponent field, otherwise all zeros. Has a significant value. M is equal to 1, exponent value e so-and-so, the numeric value is therefore so-and-so. Jesus Christ. Okay, how many pages do I have on this stuff? So you got rounding next. They go crazy on rounding. It's like even, round to the nearest even number. Floating point operations. they talk about, floating point in C they talk about, which is probably the most relevant, and then a summary. Okay, so it's not a lot. Okay. One useful exercise for understanding floating point representations is to consider sample integer values into floating point is to convert sample integer values to floating point form. For example, we saw a figure 215 that 1, 2, 3, 4, 5 is a binary representation of so-and-so. We create a normalized representation of this by shifting 13-bit positions to the right of the binary point, giving this to encode this in IEEE single precision format, we construct the fragment field by dropping the leading 1 and adding 10 zeros to the end, giving the binary representation of that. To construct the exponent field, we add a bias 127 to 13, giving 140, which is binary representation so-and-so. We combine this with a sign bit of 0 to get the floating point representation in binary. Recall from section 213 that we observe the following correlation between bit level representation of integer value 1, 2, 3 and single precision floating point value 1, 2, 3, 4. Yeah. That was the shifting. Yep. I remember that. We can now see that the region of correlation corresponds to the low order bits of the integers, stopping just before the most significant bit is equal to 1. This bit forms the implied leading 1, matching the high order bits in the fractional part of the floating point representation. So 248, I'm going to skip. $249, I'm going to skip. Okay, rounding. Let's talk more about rounding. Floating point arithmetic can only approximate real arithmetic since representations has limited range and precision. Thus, for value x, we generally want a systematic method of finding the closest matching value x prime that can be represented in the desired floating point format. This is a task of rounding operation. One key problem to solve is to define the direction to round the value that is halfway between two possibilities. For example, if I have $1.5 and want to round to maintain a lower and upper bound on the actual number, for example, we could determine representative values x to negative and x to positive, such that x is guaranteed to lie between those two numbers. IEEE floating point format defines 4 different rounding modes. The default method finds the closest match, while the other 3 can be used for computing upper and lower bounds, but you have to use assembly to access them. Figure 237 illustrates the 4 rounding modes applied to the problem of rounding a monetary amount to the nearest whole dollar. Round to even, also called round to nearest, is the default mode. It attempts to find the closest match. Thus, it rounds $1.40 to $1 and $1.60 to $2, since these are the closest whole dollar values. The only design decision to determine the effective rounding values that are halfway between two possible results. Round to even mode adopts the convention that it rounds the number either upwards or downwards such that the least significant digit of the result is even. Thus, it rounds both $1.50 and $2.50 to $2. The other 3 modes produce guaranteed bounds on the actual value. These can be used in some numerical applications. Round to 0 mode rounds positive numbers downward and negative numbers upwards, giving the value x hat such that x hat is less than or equal to x. Absolute value of x hat is less than or equal to absolute value of x. Okay. I understand these because I watched a lecture last night, so I'm just going to cruise through this. Let's speed read. Round down mode rounds both positive negative numbers downward, giving a value so and so. Round up mode both positive negative numbers upward, giving the value so and so. Round to even at first seems like is a rather arbitrary goal. Why is there any reason to prefer even numbers? Why not consistently round values halfway between two representable values upwards? The problem with such convention is that it can easily imagine scenarios in which rounding a set of data values would then introduce a statistical bias into the computation of an average of the values. The average of a set of numbers that we rounded by this means would be slightly higher than the average number of the numbers themselves. Conversely, if we always rounded numbers halfway between downward, the average of the set of rounded numbers would be slightly lower than the average numbers themselves. Rounding toward even numbers avoids a statistical bias in most real-life situations. It would round upwards about 50% of the time and round downwards about the other 50% of the time. Round to even rounding can be applied even when we are not rounding to a whole number. We simply consider whether the least significant digit is even or odd. For example, suppose we want to round decimal numbers to the nearest hundredth. We would round that value to 123 and that value to 124, regardless of rounding mode, since they are not halfway between 123 and 124. On the other hand, we would round both 1235 and 1245 to 124, since 4 is even. Similarly, round to even rounding can be applied to binary fractional numbers. We consider least significant bit value 0 to be even and 1 to be odd. In general, the rounding mode is only significant when we have a bit pattern of the form xxx.yyyy1000, where x and y denote arbitrary bit values with the rightmost y position, y being the position to which we wish to round. Only bit patterns of this form denote values that are halfway between two possible results. As examples, consider the problem of rounding values to the nearest quarter. We would round so-and-so, blah, 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 because these values are not halfway between two possible values. We would round so-and-so down, since these values are halfway between possible results, and we prefer to have the least significant bit equal to 0. Okay. I'm not going to do these problems. Oops. Practice problem 250. Oh. Okay. Oh, hey, here, math. Sorry. I was lasered in on reading here. I missed your message. How's the job hunt going? So I'm reading this book. It's the CSAPP book. Let me pull it up here. CSAPP, this one. Computer Systems, a Programmer's Perspective. And I just got through all the different numerical representation stuff. So chapter 2 was boring as hell. And I'm finishing up the section on floating point values. So I'm almost done with that. I did all these. Seriously, I did a lot of problems here. Just on different representations of, two's complement, unsigned, bunch of different stuff. And then I've been watching the lectures too. So they have the lectures online as well. So I've been going over those. Well, that's nice. How did the interview go? Do you think you passed it? So the main thing about this book is that it is focused on assembly. So this chapter 3, which is the chapter that I'm looking forward to, we'll just page through this real quick. So it starts with the machine level code. It does a lot of C stuff, but you can see that they're going to start doing disassembly. So they start showing the representation of different instructions inside the binary. So offset the bytes that encode the instructions, and then the equivalent assembly language. So disassembly over here. So the whole goal of this course is, or one of the main goals of the course is to get programmers familiar with reading assembly, not necessarily writing it. I think they acknowledge that writing assembly is like a skill of limited use at this point, but reading and understanding what the compiler generates. So this is that sum function in binary file. But yeah, being able to read assembly is a skill that is actually pretty useful, especially for like security related stuff. These are all the registers. So the next chapter, chapter 3, is going to be a good one. But right now I'm stuck finishing up floating point stuff. And I'm just trying to get through it. I'm not going to do any of the problems. Well, that's good. Hopefully you passed. What was the hardest part about the interview? Was there any like hard problems that you ran into? I think I'm on page 156. Here we are, rounding. Yeah, skipping 250. Yeah, okay. Yeah, it's not unusual that they focus on problem solving. Well, yeah, a lot of companies, they want to hire people that are good general problem solvers and have a clear way of approaching problems versus someone who has specific skills, because you can always acquire skills on the job. Giving fake scenarios and many times wrong ones, asking what you got to do if that happens. Yeah. Well, yeah, I need to start interviewing again. I I feel like I'm getting a little rusty in my interviewing skills. So I decided I'm going to start doing an interview. I'm going to interview at least one company per quarter. So I have this month to find a company and do an interview just to get the practice in. Because I interviewed for a company last year that I failed the interview for unknown reason. They wouldn't tell me why, which is a bit strange. But yeah, I realized, oh, maybe I needed to get better at interviewing. But yeah, anyways, I'm gonna skip over these problems. So, boop, boop, boop. Skip, skip, skip. So now we're on floating point operations. And I only have about 4 pages left on floating point, so we're almost done with floating point. The IEEE standard specifies a simple rule for determining the result of arithmetic operations, such as addition or multiplication, viewing floating point values x and y as real numbers in some operations, period, defined over real numbers. Let's see. But they ask about malwarebytes, which I have no idea about in terms of cores. So that I miss, yeah. What did they ask about malwarebytes? Like how many cores it takes up? I've never actually ran malwarebytes because I generally try not to have malware on my computer. I think I ran it on someone's computer one time, a Windows computer. But yeah. All right, so this is booby operator. That's what I'm gonna call this. This is the booby operator. So the computation should yield round xy, the result of applying rounding to the exact result of the real operation. In practice, there are clever tricks floating point unit designers use to avoid performing this exact computation, since the computation need only be sufficiently precise to guarantee a correct rounded result. When one of the arguments is a special value such as -0, infinity, or not a number, the standard specifies conventions that attempt to be reasonable. For example, 1 divided by -0 is defined to yield negative infinity, while 1 divided by 0 is defined to yield positive infinity. One strength of the IEEE standard IEEE standard's method of specifying the behavior for floating point operations is that it is independent of any particular hardware or software realization. Thus, we can examine its abstract mathematical properties without considering how it is actually implemented. Sorry, they ask about the basics of malware analyzing. Oh, okay. Oh, for some reason I read Malwarebytes. Versus just malware, which is what you said. Well, a good book for that is one that I have here, which is was it Linux binary analysis? This guy here. It's a small one too, so I might be doing this one sooner rather than later, because I want to learn more about ELF. But I think, my approach to answering that question would be like, well, first of all, you have two different types of analysis you can do. You have dynamic analysis, and then you have static analysis. So static is basically where the malware itself is not running, it's not executing. You inspect the binary itself, you reverse engineer it using something like IDA or Ghidra, or objdump or whatever you want to disassemble or decompile it, and then look at the decompiling result to analyze what it's doing. The other method is like dynamic analysis, where you actually run the program in a sandboxed environment and instrument all of the behavior of the program. So all the syscalls it's making, if it does any network requests, inspecting network traffic it generates, stuff like that. I'm going to start from here. Okay. Let me pull that up here. Retooling IO and unexpected journey into MS Defender's signature world. So unexpected, the page didn't load. Yeah, so they're doing like this is a hex dump. So they're just dumping out the hexadecimal of it. It looks like they're using Python here. Yeah. To decompress something. I guess some of it's compressed. Yeah, the compressed data buffer here. I've never heard of MP Engine. This looks pretty cool though. Yeah, so they're using a decompiler. I wonder which decompiler they use. They don't mention it. Maybe it's the decompile function so and so. Maybe that's what this thing is. MP Engine, is that? Oh no, is that the actual malware? Oh, is that the repo? Yeah, they're doing a lot of binary analysis here. This looks fun. Oh, cool. Yeah, it's always cool to like do the lab stuff. You get a lot of experience, hands-on experience doing labs. Have you heard of this guy? His name online is Exor EAX. Domas. This guy is insane. So he gave a bunch of talks at DEF CON, I think. DEF CON. Yeah, this dude here. Chris Domas. I would watch some of his talks. They're very entertaining if you haven't already seen them. But he does some crazy ass shit. He is insane. He has this thing, the Mobfuscator. Because move instruction in x86 64 is Turing complete, you can, like, technically it's possible to compile your program into nothing but move instructions. And so he has this compiler that compiles everything to single instruction. Well, you know, it compiles everything to moves, so it's a lot of different moves. But it's Turing complete, so it's possible. So first you were mentioning about the roadmap, seeing this article. What do you recommend me to build the roadmap? That's a good question. I'm in a process myself of like deciding how to build the roadmap for my learning, if that's what you're talking about. I forget what we're talking about roadmaps for, but like we only have so much time on this planet to like learn and grow and develop as people, and you have to prioritize things. So I might have recommended this book, which is KNRC, which I finished reading. Let's see, K and RC. Like, this is like a book that most people have read in software if they know what the fuck they're doing. It's not the most up-to-date book on C, but it is a point in time. It was written in a point in time when C was like being popularized, and so it's a common touchstone for a lot of people. So that's like a good place to start, is getting really good at C. Roadmap regarding from noob to professional in malware form, from analyzing to writing my own. Well, I mean, this is like a path that I haven't walked myself, so I can't really give you the exact like parts of the like path that I would walk, but I can just tell you like how I approach doing it myself, which is to go online and just find people who you respect in the field. So people who are doing malware research or malware development, if that's what you want to get into, and just start reading their writings. You know, if they recommend books, like some of these people, they have like book sections on their website. Like, what's a good example? Brendan Gregg. Like, he has a section on his website just for books. What was it called? Books down here, recommended reading. And so like what I've been doing is I literally just look through his bookshelf and I'm like, okay, I can see things that would be valuable for my learning process. So I mean, this is like a massive list of like stuff that he's read and recommends, but some things, this is where I got that binary analysis. I think it was here. It was actually, I think I got it from looking at his bookshelf. This one here, Learning Linux Binary Analysis. He doesn't actually recommend it on his page here. But this is more stuff that I'm interested in. Maybe the computer security section would be something you're interested in. But what I'm getting at is like the methodology is like find people that are well respected, that have accomplished a lot in the field that you're interested in, and do research. Do your own research into like what books they recommend, what learning resources they recommend, and that will just naturally like put stuff into your queue to like consume. Yeah. So that Linux binary analysis book, if you pick that up, that would be fun because I'm going to be reading that soon. These are some of the ones that he recommends, like Hacking Exposed. I've never actually read any of these. Applied Cryptography I've heard of by Bruce Schneier. But this is very dated. Yeah, like the most up-to-date book he has recommended here is Hacking Exposed. What I hear from people in the community, the software security, information security community, is that hacking books get out of date really quick. So some books I imagine are going to be timeless and foundational. Cryptonomicon, I've never actually. That is like more of a fiction book, yeah. I would skip that one. um, let's see what else he has in here. But yeah, find people that you respect, figure out where they learned from, and then find those resources. And go technical, go super technical, because there's going to be a lot of like stuff that you find that are like managerial books or organizational books, or books related to software and information security that are not technical, and you want to go technical. Like if you want to get fucking good at computers, like you want to read the technical books. You don't want to read the bullshit books. The Linux binary analysis, it's just this one here. Learning Linux binary analysis. And it's this guy, he's the ELF master. So ELF is the binary format on Linux. So that's why he calls himself the ELF master. There's ELF, which is like the packaging format for binaries on Linux, and I think a lot of Unixes use it as well. And then there's Dwarf, which is an extension that is used for debugging. So there's like a Tolkien like naming convention in Linux around binaries. But I mean any binary like let me just create a terminal here. So if you do which on cat, let me zoom in a little bit. So if I do like file on user bin cat, you can see how it says ELF. So it's an ELF binary. I think it's extensible linkable format or something like that. But yeah, this is the book that I was talking about. But binary analysis is only one part of malware analysis. The other book that I've purchased is called the Ghidra book. And this one isn't out. So there's a second edition that's coming out. It might... yeah, I think it's still pre-ordered. Yeah, it's still on pre-order. So this is the other book that I would recommend. There's a first edition out right now that you can probably find, but the second edition is coming out in a couple of days. It's not too far away. Yeah, March 31st. So at the end of the month. And this one is about using Ghidra. So Ghidra was a tool developed by the NSA. It runs on the JVM, and basically allows you to like decompile and reverse engineer binaries, and it's similar to IDA. So IDA is the other. Yeah, IDA Pro is the other tool. It's similar. It's similar to Ghidra, but IDA Pro is commercial. I think it's like it's not cheap either. You can find like a disassemble most everything, effortless high quality disassembler output. Does pretty good at decompiling. I've heard a lot of good things about it. I've never ran it myself because I don't pirate software, and I don't pay an insane amount of money for yeah, look at this. I guess I can do individual non-commercial use. There's IDA free, and then there's IDA home. So you get the x86 32 and 64-bit disassemblers, no ARM, any Mac, Linux, or Windows. And then this one, I wonder if that means that you can I guess you can't disassemble or decompile a ARM. You would need the you get one disassembler of your choice. That's a bummer. 2 cloud-based decompilers from the same family, matching the selected disassembler. So you're only getting basically I would go with the free route for x86 64, and then if you needed ARM, then you would have to pay for it basically. But anyways, yeah, the IDA Pro is like another popular one. This guy here. Is there any open source one except Ghidra? Ghidra is the only one I'm familiar. Oh, there was another one that I ran across like last year. I forget the name of it though. I forget the name of it. I mean, GDB as well. Like, I actually have this. If you jump over to learn log, oops, yeah, and then was it Vim, README, GDB? I found this thing, which is B's quick guide to GDP. This thing here. Yeah, if you're not familiar with GDB, it's also a really useful tool. It uses ptrace system call to intercept execution of programs. Yeah, getting familiar with a debugger and using a debugger to like dynamically analyze programs, that's like important. Ghidra, I don't know if Ghidra does ARM or not. Oh, I have it on here. I think I have it on here. Ghidra, yeah. The thing I don't like about Ghidra is that it's JVM. You have to create these stupid projects. Support. No. I've never actually read their documentation. I imagine it supports ARM. I don't see why it wouldn't. I try to debug Malwarebytes, but somehow I don't connect to it. Somehow security. Yeah. Um, I'm not really familiar with the Windows protections in place, but a lot of times when you try to attach a debugger to a program, you have to have the right permissions to do that, unless it's a child process. Like in Linux, you have to have this thing called cap sysadmin or cap ptrace, which are like Linux capabilities. I'm sure Windows has something similar to prevent arbitrary debugging, because I mean, debugging capability itself is like a attack vector. So you want to definitely only be able to debug stuff that you should have access to. All right. I can't find where it says what architectures they support, but I think they support ARM. There was one I saw last year, GitHub Mac. I think it was a Mac OS disassembler. No. Decompiler? This one. Yeah, this one. It's for Mac. But this was like one that someone recommended to me. Yeah, and I looked her up. She's actually pretty sick. She does the YouTube stuff. If you look her up on YouTube, she has like a lot of really awesome YouTube stuff. YouTube. Yeah, here. Yeah, she does a lot of stuff on YouTube. Hey, look, it's KNR right there. But yeah, her she has this. Oh, she does Ghidra stuff too. Yeah, I forgot about this. So she has a embassy server for Ghidra, Malmite. Yeah, this thing here. iOS and macOS decompiler designed to help researchers analyze and decode IPA files and application bundles. Both the topic Ghidra, so it uses Ghidra decompilation to offer direct support for Swift, Objective-C, and Apple resources. So yeah, I feel like Ghidra is like the tool that people are moving towards. Like IDA Pro is like the commercial like standard, and then Ghidra is like the tool that most open source is like moving to. So I'm excited for this book launch, the second edition of the Ghidra book. The Ghidra book. Once this arrives, I'm gonna dive into it. Yeah, I guess you wrote MCP for Ghidra, yeah. But yeah, I would follow her on YouTube if you want more like disassembly, decompiling stuff. She does a lot of stuff. Cool. All right, I'm gonna get back to reading here. Where did we leave off? I forget. Oh, okay, we left off here. So I'm here at we saw earlier that integer addition both unsigned and two's complement forms an Albion group. Addition over real numbers also forms an Albion group, but we must. So Albion group basically is like a modular arithmetic, from what I understand. So addition over real numbers also forms an Albion group, but we must consider the effect of rounding has on these properties. I don't really care about any of this. This is important. So the lack of associativity in floating point addition is the most important group property that is lacking. It has important implications for scientific programmers and compiler writers. For example, suppose the compiler is given the following code fragment: x is equal to a, b, c, y is equal to b, c, d. The compiler might be tempted to save one floating point addition by generating the following code, where it adds b, c first, and then uses that sum for both to add a to it and d to it. However, this computation might yield a different value for x. basically the associativity is lost, so you can't group together like B and C, because A and B need to be evaluated first before C can be added to it. And the reason why is like say A is like like a really high number, and B is a small number, and C is also a small number. Actually, that's a bad example. Basically, like you can't add, because you don't have infinite precision and you only have a certain range of values in floating points. Eventually, you're going to hit things like rounding errors and infinities, in which case additional computations on those values then are kind of screwed up. So you can't rearrange things, because the order in which they're done actually has a really important effect on the outcome. Because you might run into one of these affinities based on the ordering. So yeah, let's continue. However, this computation might yield a different value for x than would the original, since it uses a different association for the addition operations. In most applications, the difference would be so small as to be inconsequential. Unfortunately, compilers have no way of knowing what trade-offs the user is willing to make between efficiency and faithfulness to the exact behavior of the original program. As a result, they tend to be very conservative, avoiding any optimizations that could have even the slightest effect on functionality. On the other hand, floating point addition satisfies the following monotonicity property. If A is greater than or equal to B, then x plus floating point addition of A is greater than or equal to x plus floating point addition with B. So basically, adding x to both of the operands in this inequality is going to result in the same inequality holding true. So that's for any values A and B and x other than nan. This property of real and integer addition is not obeyed by unsigned and two's complement addition because of the overflow and underflow situations. Because you can go from very high integer in a two's complement representation, and then you get wrapped around to a negative value. Floating point multiplication also obeys many of the properties one normally associates with multiplication. This operation is closed under multiplication, although possibly yielding infinity or nan. It is commutative, and it has 1.0 as a multiplicative identity. On the other hand, it is not associative due to the possibility of overflow or the loss of precision due to rounding. So that's exactly what I was saying. You can either overflow into infinity, or you might have to deal with the rounding issues. For example, with single precision floating point, the expression, yeah, this is a good example. So 1e to the 20th times 1e to the 20th is such a huge number that it overflows. And then you multiply that times the negative 20th, it's already at infinity because of this evaluation resulted in infinity. Even though these two things negate each other, like these two operations here, multiplying by this and then multiplying by its inverse, negate each other, and this value is representable in the range of values. Even if that's true, the infinity got hit here, and so everything's infinity after that. But if you put the parentheses around these two things, they evaluate to 1, and the end result is just 1e to the 20th. So in addition, floating point multiplication does not distribute over addition. For example, the single precision floating point, the expression 1e to the 20th evaluates to 0, while 1e to the 20th with the distribution evaluates to a nan. So you can't distribute without hitting these weird situations, potentially. On the other hand, floating point multiplication satisfies the following monotonicity property for any values of A and B and C other than nan. Okay, I'm not going to review that. We're also guaranteed that A times A is greater than or equal to 0 as long as A is not equal to nan. So that means that if A is negative, it becomes positive. And if A was positive, it continues being positive. and that holds true if a is infinity or any other value, even if it's 0. As we saw earlier, none of these monotonicity properties hold for unsigned or 2's complement multiplication. This lack of associativity and distributivity is of serious concern to scientific programmers and to compiler writers. Even such a seemingly simple task as writing code to determine whether 2 lines intersect in 3-dimensional space can be a major challenge. So now we get to floating point in C. All versions of C provide 2 different floating point data types, float and double. On machines that support IEEE floating point, these data types correspond to single and double precision floating point. In addition, the machine use the round to even rounding mode. Unfortunately, since the C standards do not require the machine to use IEEE floating point, there are no standard methods to change the rounding mode or to get special values such as negative infinity, positive infinity, -0, or nan. Most systems provide a combination of include.h files and procedure libraries to provide access to these features. I mean, you could do it just with like bit shifting and casting. Like let's get a negative. I'm gonna do a test program here. Let me wait a minute. Yeah, let me kill this. I'm gonna kill this Python session down here. Okay, and then let's see, what chapter 02? I think that's where we're at. Yeah. So I'm gonna say test generate weird float values .c. So let's just do some includes here. Standard io.h and standard lib. And then in here, I'm going to say, let's take a 64-bit, and let's just do a 32-bit integer. So say we have a unsigned int, which should be 32 bits. And we initialize that to 0. But I actually want to do 0x. And then I want to do 8 zeros, so that's 1 byte, 2, 3, 4. So that's 1, 2, 3, 4. And we need to give it a name, obviously. We'll just call it X. So what that does is that sets the sign bit to be negative, and everything else is 0, which will give us a 0 value. So if I do printf, I doubt this is even able to be printed out, but we'll see. %f, I'll just say value is equal to that, and I'll give it x. Why does it not like, it says format says type double, but the argument type unsigned int. Okay, so this is where we need to convert the value to a different type. And we can't just do a normal cast, because the cast would involve a actual conversion from the integer value to, so we get a different bit pattern out basically. So I think what I need to do is say, hey, let's get a reference to x. So now we have this pointer, and we're going to say, hey, you're actually a pointer to, instead of being a pointer to an integer, you're going to be a pointer to a float. And then we're going to dereference that. So I think that's the syntax we want. And that makes the compiler happy if we make that. And we run our build test weird. What is it? What did I call it? Generate weird float values. So that, yeah, that got us our -0. So we can get -0 out that way. So now what we want to do is manipulate this x value, and we can then continue to print it out, and we just keep on reinterpreting it as a float. So what's the next value I wanted to try to do? So 8 bits being the exponent would give us negative infinity. So we need 9 bits. So this would be F, and then this would be 8. So I think this is negative infinity. So this will be, we'll call this thing negative 0. This would be negative infinity. So that is not negative infinity. That's a actual really big value. So let's try to figure out why. Oh, because I did a 9 instead of an 8. I meant to do an 8. That still didn't do it though. Okay, so the floating point, 32-bit floating point has, I thought 8 bits. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. So if we wanted to represent 0, it'd be 8 bits, or 9 bits set, and then all zeros would be the negative infinity. So I'm trying to think why this is messing up. So F sets 8 bits, all the ones. No, it sets 4 bits. That's where I messed up. Okay. So I need FF. So now 8 bits are set, and then I need another 1 bit here, which would be 8. So that should be negative infinity. Yep. So we got negative infinity out. If we want positive infinity, then this F would have a 0 on its most significant bit, which would make this 7. 7F. So this would be positive infinity. Make. Yep. If we want a nan value, we just have to have a bit set in the fractional part. So this would be a nan. Look at that. What else do we want to do? I think that's about it for weird values. Negative 0, negative infinity, positive infinity, nan. I guess, can I get a negative nan? Let's try that. So this would be FF. Negative nan? I don't know if that will work, to be honest. Hey, we got a negative nan. And we'll reorder these just so that the negatives come first. We don't need to do positive 0 because that's just 0. That's an easy one. Cool. Well, that was fun. So we were able to just use bit patterns and a reinterpretation of those bit patterns as a float and printf to generate all of the weird values in floating point that you normally don't encounter. Like there is no infinite, like node. If I run node, there is a like negative infinity. Like that is an actual symbol that you can type in, and it gives you back the floating point value for negative infinity. But in C, what they were saying in the book is that there's no actual value that you can do. You have to kind of play with the bits. Okay, so where are we at now? This is a floating point in C. Yeah. So say most systems provide a combination of include files and procedure libraries to provide access to these features, but the details vary from one system to another. For example, the GNU compiler GCC defines program constants infinity and nan when the following sequence occurs in the program file. Okay. So you have to include math.h with the GNU source or default source set to 1. Practice problem 253, fill in the following macro definitions to generate a double precision values so-and-so. You cannot use any included files such as math.h, but you can make use of the fact that the largest finite number can be represented with double precision is around 1.8 times 10 to the 308. Okay. I guess we could do some math, but I'm going to avoid doing math and just do the bit patterns. So I'm actually going to do this problem. So this is 253, because I kind of already did it just now in this test generate weird floats. So I'm going to do a different one now. I'm going to do a unsigned long, which should be 64 bits. So that's 8 bytes. That's 2, 3, 4. Oops. 5, 6, 7, 8. And I'm going to call this thing Y instead of X. And then here, they're talking about defining, doing a pound define. Okay, we'll do a pound define. Pound define positive infinity. And then we got negative infinity, neg, and negative 0. So negative 0, I can just define these here, right? So that is negative 0 right there. Negative infinity is going to have how many bits? I think 11. So 11 plus 1 would be 12. So this is going to be F. That'll set 8 bits. Or no, it sets 4. That sets 8. And then another 4. So it'd be 3 Fs. I think that's negative infinity. And then positive infinity would have 7 here. Okay. Let's see if these pound defines work. And we need to interpret these as oh shit, I can't do that, can I? It's hard to do these as macros because you don't have a thing to reference. I guess what we could say is like, hey, take a reference to this. Now it's a pointer. Whatever type you gave it, I'm going to give it a new type, which is going to be a pointer to a double. And then we're going to dereference that. I think this will work, hopefully. Okay, let's try printing these out now. So we'll say double positive infinity. And then here we're just going to say, hey, actually you're going to be positive infinity. This all depends on whether you can take a reference to a constant. Can I take address of R value type long? Exactly. You can't do that. Damn it. What we could do is make these globals and then take a reference to them. So I'm going to say underscore underscore pause infinity. And we'll make this thing what? It's going to be unsigned long. Yeah. And then we could take a reference to positive infinity like that. Sorry, I need to have an equal sign here. Comment those out for now. And then make. And then we'll build it. Test. Generate weird stuff. Okay, so that did create the positive infinity that we expected. The problem with this is that like we're also wasting a tiny bit of memory in like a global area here. Unsigned long neg infinity is equal to that value. And then this will be negative infinity. And then the last value will be unsigned long -0. -0. So all the chip manufacturing companies have malware analysts in their companies to search for malware, so they do that on assembly level. I'm not sure, to be honest. But yeah, I mean, yeah, that would be a really interesting job, doing malware analysis for like a CPU company like Intel or something. But yeah, I do not know what they're doing that, but I imagine it's gonna be some assembly. I mean, especially if it's a CPU chip. Like you need to know what instructions are being ran on the CPU. So that's gotta be assembly. All right. Let's go ahead and print these out. It says double negative infinity and double -0. So we'll say negative infinity, -0. So I bet you the way that they're doing this in the book is going to be totally different. They're probably going to use some type of like expression that evaluates to that value. But the problem with that is that like I don't know if the compiler is gonna be able to optimize that away. It possibly could, but what is this thing complaining about? Oh, because I got a semicolon up here. There we go. All right, so let's go ahead and make this up. Okay, everything. Wait a minute. Negative and positive infinity got switched. Why? F should be negative. Wait a minute. Did I mess this thing up? Oh, I messed it up here. So that's going to be... Let's just switch it like this and say... negative and positive. Okay. So you have double positive infinity, double negative infinity, double -0. Well, what I have, get to know that it going to be piece of cake for you when you do malware. Yeah, I guess I don't know. I'm not really interested in malware right now. My whole desire to I guess it might be fun to do some malware stuff at some point, but I don't know. My whole goal with learning assembly is I want to learn more about how our computers actually operate and less about like how malware operates. Like if I got really good at that type of stuff, I would want to do something other than security. I would want to use it for like reverse engineering for like good reasons and less for security related stuff. All right, so everything's working here. I'm gonna open up my problems, go down to the bottom here. I'm just gonna read in my what is it called, test generate weird float values. And I'm just going to take these things at the top here, is what they were asking for. And say C, do that. Okay, let's go to the back of the book now, or the back of the answers, the chapter, and make sure that we got the right answer. 253. Oh, they did it a really lame way. Yeah, I like my way better. So if you go all the way, it was a page 196. Nope, went too far. Here it is. This is what they did. I mean, arguably their solution is preferable because it's all done. I bet you the compiler is able to optimize these, like the negation operations, so it doesn't have to happen at runtime. The other thing is that like my solution like uses global memory that's mutable potentially, and so these values could change. I guess they would get copied, but every time, I don't know. I think my solution is a little bit suboptimal in that it uses extra memory. Like this memory has to stick around. I don't think the compiler can optimize it away. And I think the compiler can optimize away the math being done on the values here. So I'm going to say I decided to do this with bit patterns because the other way was too lame. No. We'll just say because it was fun to do it this way. Problem. This approach that let's see, we're wasting 8, 16, 30, 24. Okay. Let's go back to the section that we were reading. Which was... I got lost. Floating point in C. Rounding. Floating point in C. Okay. When casting values between int, float, and double formats, the program changes the numeric values and the bit representations as follows, assuming data type int32. From int to float, the number cannot overflow, but it may be rounded. From int to float to double, the exact numeric value can be preserved because double. Sorry, from int or float to double. Yeah. The exact numeric value can be preserved because double has both greater range as well as greater precision. From double to float, the value can overflow since the range is smaller, otherwise it may be rounded because the precision is smaller. From float or double to int, the value will be rounded towards 0. Furthermore, the value may overflow. The C standard do not specify a fixed result in this case until compatible microprocessor designate the bit pattern so and so for tmin as an integer indefinite value. Any conversion from floating point to integer that cannot assign a reasonable integer approximation yields this value. Weird. That's weird. Thus, the expression int plus 1e to the 10th yields the negative value, generating a negative value from a positive one. Yeah. That is weird. All right. Assume variables x, f, and d are type int, float, and double, respectively. Their values are arbitrary except that neither f nor d equals positive or negative infinity or nan. For each of the following C expressions, either argue that it will always be true, evaluate to 1, or give the value for the variables such that it's not true, evaluate to 0. Let's go ahead and do this one. This one sounds fun. So 2.54. And we have A, B, oops, C, D, E. So we have this expression x is equal to int double x. So we go from an integer to a double back to an integer. I'm going to say true. True, no rounding. No chance of overflow. No loss. Yeah, I just say no rounding, no chance of overflow. B, so we go to a float. Let's say false. And I could do this in like a, if I create a, let's do this, Clang REPL. And in here, I'm just going to say include, oops, damn it, include standard IO. And then we're going to do a printf of percent. In this case, it's going to be D. And we're going to give it a value that is the int float of some numerical value. So I'm going to say a very large numerical value. I'm going to say 0x. And then we're going to say 7 f ff ff ff. So if we just converted that to an integer, we would get that huge value out, but when we go into a float, we lost. So if this was like an int here, you can see how it doesn't matter. So this value represents the maximum value for an unsigned, or a signed integer, I should say. Maximum value for signed integer. So they wanted a value for x that is a counter example. So I'm just going to grab this one, paste it in here. All right, C. So that is double float D. So you're going from a double to a float back to a double. False, loss of precision. I'm not even going to give a counter example. This will be false. Loss of precision. D, we're going to go from float to double back to float. True, no. I'll just say the same thing here. D, E, F is equal to negative F. Yeah, that's true. Just flipping the assigned bit. Okay, let's look at the answers. Yes, no, no, yes, yes. Yep, that's exactly what I got. Cool. Let's continue on. We're at the summary. Oh, we got more values. We got F, G, and H. I didn't even look at those. Let's do those. F, G, and H. So f 1 divided by 2 is equal to 1 divided by 2. I'm going to say yes because they both force... yes, because they both force floating point division. And the operands are converted to floats. Or doubles. Was there any problem which discusses about optimizing the code for better processing? Not that I've run into so far. Maybe next chapter. Next chapter is more about that type of thing. Let's see here. I do want to experiment and test this. So if we do printf, and I'm going to give it, we'll do it as a float. 1.0 divided by 2 is equal to 1 divided by 2.0. Oh, and these need to be like this. %f. Yeah, they're going to be the same. Yeah, like I said. G is d times d is greater than or equal to 0. True. I'm going to say true. True, because all negative values will flip positive, and if they overflow, they will become positive infinity. H is f plus d, so a float plus a double, and then minus the double. No, because technically the double could be at the boundary where it's about to overflow, and then adding the float actually takes it to overflow territory. So I'm gonna say no. False. D could be at the boundary where it is about to overflow, and F puts it to infinity. And then we say, in which case subtracting F will still return infinity, which is not equal to D. EQUAL to D. Okay, so let's check the answers on those. So I did true, false for F. True, false. Yep. Cool. So that's all the problems for this chapter. So I can exit out of there. He said, so I have a question. When they release a new generation and optimize performance apart from the NM, do they... Sorry. Let me reread what you said here. I guess... I guess, I don't really know the specifics. Generally speaking, though, application code that is running on existing Intel or AMD 64 chips, the goal of the chip manufacturer is to improve performance without changing the code. So if you have application A, you want to ship a chip that either has a higher clock frequency or has more parallel execution cores or does some type of superscalar magic, some out of order execution, some pipelining, some speculative execution. Like the CPU manufacturers have all these like techniques to like get more performance without having to modify the code because they don't have access to the code. But there is this thing called microcode that's in the CPU, which they modify a lot as part of their release. So that is part of the release and performance considerations. This stuff here, which I've never written microcode myself, but it's part of the microarchitecture of the CPU. Basically, it's a computer underneath your computer. And they'll do all these like all this testing, benchmarking, and stuff. Sometimes they release new instructions, and to take advantage of those new instructions, the software has to be rewritten, or the compiler has to add support for it. So like in those situations, yeah, like the software has to be recompiled or rewritten. Microcode, I don't know what languages. There's VLA, I think is I honestly don't know. What is the language used to write microcode for Intel? VLIW. I was close. I said VLA. It's VLIW. Intel microcode is written in a proprietary, low-level proprietary machine language or assembler that translates into VLIW like very long instruction word micro operations. This proprietary, undocumented, and encrypted code manages hardware-level actions like register transfers and ALU operations, while not public. Researcher tools often refer to this specialized assembler as generating micro-op sequences, or sometimes using specific limited instruction set termed XU code. Yeah, I mean, this stuff is like massively proprietary. Yeah, I mean, it's all proprietary. They invent their own stuff. No, I mean, it's probably a trade secret, but if you and I got access to it, we couldn't make our own CPUs. Like, in order to make a CPU, you have to have a fab, like a fabrication facility. It's like really costly. Like, I mean, you could use like TSMC or whatever to make a CPU, but generally speaking, like, I mean, good luck doing that. If you're doing that, you have like funding for the business to do it. But Intel's competitors, like AMD, huge competitor of Intel, but even like ARM, TSMC itself is a competitor to Intel because Intel runs its own fabs. Yeah, all the competitors, NVIDIA, I guess, I would consider a competitor to Intel. Like they have all these like trade secrets because they want to have a competitive edge against their competitors, not because like you and I can actually do anything with it. All right, let's read the summary and then we'll be done with this chapter. It's a milestone for me, getting done with this stuff. All right, computers encode information as bits, generally organized as sequences of bytes. Different encodings are used for representing integers, real numbers, and character strings. Different models of computers use different conventions for encoding numbers and for ordering the bytes within a multi-byte data. The C language is designed to accommodate a wide range of different implementations in terms of word sizes and numeric encodings. Machines with 64-bit word sizes have become increasingly common, replacing 32-bit machines that dominate the market for around 30 years. Because 64-bit machines can also run programs compiled for 32-bit machines, we have focused on the distinction between 32 and 64-bit programs rather than machines. The advantage of 64-bit programs is that they can go beyond the 4 gigabyte address limit of 32-bit programs. Most machines encode signed numbers using a 2's complement representation and encode floating point numbers using IEEE standard 754. Understanding these encodings at the bit level, as well as understanding the mathematical characteristics of the arithmetic operations, is important to writing programs that operate correctly over a full range of numeric values. When casting between signed and unsigned integers of the same size, most C implementations follow the convention that the underlying bit patterns do not change. On a 2's complement machine, this behavior is characterized by functions t to u and u to t for w bit value. The implicit casting of C gives results that many programmers do not anticipate, often leading to program bugs. Due to the finite lengths of the encodings, computer arithmetic has properties quite different from conventional integer and real arithmetic. The finite length can cause numbers to overflow when they exceed a range of the representation. Floating point values can also underflow when they are so close to zero that they are changed to zero. The finite integer arithmetic implemented by C, as well as most other programming languages, has some peculiar properties compared to true integer arithmetic. For example, the expression x times x can evaluate to a negative number due to overflow. Nonetheless, both unsigned and 2's complement arithmetic satisfy many of the other properties of integer arithmetic, including associativity, commutativity, and distributivity. This allows compilers to do many optimizations, for example, in replacing the expression 7 times x by x bit shifted over by 3 minus x. We make use of the associative, commutative, and distributive properties along with the relationship between shifting and multiplying by powers of 2. We have seen several clever ways to exploit combinations of bit-level operations and arithmetic operations. For example, we saw that with 2's complement arithmetic, the negation of x plus 1 is equivalent to the negative x. As another example, suppose that we want a bit pattern in the form of all zeros and then all ones for the second half, consisting of w minus k zeros followed by k ones. Such bit patterns are useful for masking operations. This pattern can be generated by the C expression 1 bit shift over k minus 1, exploiting the property that the desired bit pattern has a numeric value 2 to the k minus 1. For example, the expression 1 bit shifted over 8 minus 1 will generate the bit pattern 0xff. Floating point representations approximate real numbers by encoding numbers in the form of x times 2 to the y. IEEE standard 754 provides for several different precisions, with the most common being single 32-bit and double 64-bit. IEEE floating point also has representations for special values representing plus and minus infinity, as well as not a number. Floating point arithmetic must be used very carefully because it only has limited range of precision and because it does not obey common mathematical properties such as associativity. There's an aside here we can read. Computers really are so complicated. I never knew that there is microcode in the first place. Yeah. When I started my career, I actually didn't go to school for any of this. I'm self-taught. I did take undergrad courses in computer science after I had already started my career. But for the most part, I was self-taught when I started. And what I realized is that computing is like an infinite landscape that you can spend your entire life exploring. And I had never encountered that in anything that I've worked on previously. Like there's so much interesting shit going on with computers. It never ends. But the amazing thing about computers is that we built every single bit of them. Every single aspect of computers is human made until AI. But we have constructed it. It wasn't something that was given to us. It's not like our biological heritage through evolution. Like, it's not a biological system that has been evolving over like, billions of years. Computers are things that we have created. And so every bit of them are understandable. Because if they weren't understandable, a human being wouldn't have created them. Now that we're in the AI era, that may not be true moving forward, because AIs can create things conceivably that humans can't conceive. But for the most part, everything about computers you can understand. And with open source, the source is available. There's no excuses, And one of the funny things that I heard recently is that when you learn assembly and you learn binary analysis, it's almost like the entire world becomes open source to you. Because you could just pop open Ghidra and like disassemble and decompile like programs and figure out what they're doing. Like, you don't necessarily need the source code, which I'm looking forward to having more confidence in that. But for the most part, all the cool technology is already open source. Like all the compilers, all the operating systems, web browsers, all the server infrastructure, all of it's open source. All the programming languages. Like, when's the last time you used a proprietary programming language? No one does. It's all open source. The source is available. It's just up to you to like have a desire to want to understand it. That's been my limiting factor in my career, is my desire to want to understand things. And it oscillates, not gonna lie. I'm gonna clip it. Yeah. Cool. All right. Oh, thank you. Yeah, appreciate it. All right, so we're at the end of this chapter. I was going to read this aside. And then, let's see. It's almost 5. I think I'm going to hop off after I read this aside. And then I'll hop back on this evening probably just to get some more reading done on chapter 3, because I want to start making some progress on that. Cool. So let's read this aside. The high cost of floating point overflow. Converting large floating point numbers to integers is a common source of programming errors. Such an error has disastrous consequences for the maiden voyage of the Ariane 5 rocket on June 4th, 1996. Just 37 seconds after liftoff, the rocket veered off its flight path, broke up, and exploded. Communication satellites valued at $500 million were on board the rocket. A later investigation showed that the computer controlling the inertial navigation system had sent invalid data to the computer controlling the engine nozzles. Instead of sending flight control information, it had sent a diagnostic bit pattern indicating that an overflow had occurred during the conversion of a 64-bit floating point number to a 16-bit signed integer. The value that overflowed measured the horizontal velocity of the rocket, which could be more than 5 times higher than that achieved by earlier Ariane 4 rocket. In the design of the Ariane 4 software, they had carefully analyzed the numerical values and determined that the horizontal velocity would never overflow a 16-bit number. Unfortunately, they simply reused this part of the software in the Ariane 5 without checking the assumption on which it had been based. That's a cool little story. Always check your assumptions and comment your code, because people who come after you need to know what the hell you're thinking about when you wrote it. All right, cool. I'm going to hop off here, get some dinner, chill for a little bit, and then I'll be back on later this evening to start on chapter 3. Actually, you know what I might do? There are these labs that the course has. So I might do the lab for chapter 2 before I start on chapter 3. So I'll do one of those. I'll either start on chapter 3 or I'll start on the lab for chapter 2. Cool. All right, I'm going to hop off here. It's nice chatting. I'll be back this evening for a little bit. Cool. See ya.